Hey everyone, welcome back to AP Precalc. This is lesson 2.11. Let's get right into it. All right, so here's the bell ringer for today. Pause the video if you haven't done this already, because I am about to go over the answer. And so an exponential function is in the form of f of x or y equals b to the power of x, where b is greater than 1, so it's got to be a positive number, and it has the given point of 2, 81. Find the inverse equation. So first we wanted to see if we can find the equation. So let's plug in that point and see if we can solve for b. So we have b to the power of x, which in this case is 2, and this will give us an output of 81. So what squared gets us 81? That's either going to be positive or negative 9, right? Should be our b value. However, we know b is greater than 1, so we know b has to be positive 9 here. So now we know f of x is equal to 9 to the power of x. But we want to find the inverse. So remember, if you have b to the x, the inverse of that is log base b of x. Those two are inverses. So then here, our inverse equation should be log base 9 of x there. All right, so today we're going to be learning more about logarithmic functions and their general graphs. Because logarithmic functions and exponential functions are inverse of each other, they're inverses, the characteristics will also have an inverse relationship. For example, they're a little different than exponential functions because you can't take the log of 0 or a negative number. And so let's take a look at the general shape of a logarithmic function by graphing 2 to the power of x and then finding its inverse graphically. So here, if you plug in 0, 2 to the power of 0 is 1. Then you plug in 1, you should get 2. 2, you should get 4. 3, you should get 8, and so on and so forth. And so the exponential function should look a little something like that. And now if we take our line of reflection, which that looks good enough for me, and then we graph the inverse, right? So that was, now let's graph log base 2 of x, and we just graphed 2 to the power of x. And so here we're going to take the inverse points, so 1 comma 0, 2 comma 1, 4 comma 2, 8 comma 3, and then here, as we looked at last time, you could see we know that the horizontal asymptote here is going to be reflected and become a partial or a vertical asymptote for that logarithmic function there. So that's something to kind of be on the lookout for. And because there's a vertical asymptote there for that logarithmic function, we now know the domain of this has to be, x has to be bigger than 0. Which makes sense because the range of this exponential function is x is greater than 0, right? There's no y value where it's greater than 0, and so, or this should be y for the range. And so remember, the domain for one function will become the range for the inverse function. So that's kind of what I wanted to show here. All right, so there's a few key characteristics with logarithmic functions. What's nice about this is with exponential functions, there is 4 different types that you had to kind of remember the shape of: exponential growth, exponential decay, and then both of those functions but flipped. You won't have to worry about 4 this time. It's just going to be 2 main logarithmic functions. The first one will look like that, and then the second one will look like that, both of which having a vertical asymptote at x equals 0. So it's going to be this general form, f of x equals a log base b of x, where b is just going to be a number greater than 0, and a is not 0, b is not 1. We talked about those domain restrictions last class, so go watch 2.10 if you forgot those. The domain for a logarithmic function is x is greater than 0. And then the range, though, however, is not restricted like an exponential function, but is kind of, you can plug in, or you can hit every single y value. This is going to shoot up forever, and so that's going to cover positive infinity. And then this actually will be decreasing forever, So that's going to approach every value all the way to negative infinity there. So those are the two main graphs. The key characteristics, though, is this one is going to be where a is going to be greater than 0, and this one is where a is less than 0. Both of them have b is greater than 1, so that's not going to be a defining characteristic. It really just becomes, is a positive or negative, is the only thing you're going to look at. Remember, this is a log base b of x. So a is just that coefficient out front. If it's positive, it's going to look just like that general graph. If you just remember the general shape for log base 2 of x, where it's just like positive 1 log base 2 of x, it should look like that. Then you should be good. Knowing that a is negative then, though, however, we'll flip it because this is a vertical reflection, is what a negative number out in front does. And so it's going to flip that whole graph vertically, where it's going to behave like this graph there. So just know if a is positive, it's going to be increasing. If a is negative, it's going to be decreasing there. All right, so take a few minutes now, fill in the blanks with statements about the function shown above. Pause the video and try this on your own because I'm about to reveal the answers. All right, so here are the answers. Let's go over these. The first one here is this is an example of a logarithmic function. The main thing that we can tell is that this is getting closer and closer to negative infinity as you approach 0. That's always going to be the case with a logarithmic function. Don't get this confused with the exponential function, which will actually cross the y-axis there. So be cautious of that. So it is logarithmic. It's a value in the form of a log base b of x. A should always be a positive number when it's shaped like that. Its base is a number that's greater than 1. So positive and greater than 1. It's always going to be increasing. So it's always going up. Never going to be going up and then all of a sudden go down. Because of that, it's always going to be concave down. So shaped like that, downwards U-shape. It's also always going to have no relative extrema. So that's what I'm kind of talking about when I say it's always increasing. It's not going to be increasing and then decreasing, producing local mins and maxes. That won't be the case. You won't see that. So you don't have to worry about that there. The next one, there are no points of inflection because it will never change concavity, or there won't be any peaks or valleys to find them between. As x approaches 0, so remember this is where x is 0, from the right-hand side, so coming in from the right, this is shooting down to negative infinity. That's what the y values will approach. As the x approaches, or as x increases without bounds, so as x goes to the right forever, this is going to be shooting up to infinity. It's going to be pretty slow growth, but it's still going to be growth. So don't be confused by that. It's still going to positive infinity. And then the domain is from 0 to infinity. You just can't plug in any number that's either 0 or a negative number there. All right, so these are the key characteristics of logarithmic functions. I'm going to go through each one of these in a little bit more detail. All right, so increasing versus decreasing. Logarithmic functions, the two types that you'll see, will either always be increasing or it will always be decreasing. It's not going to be increasing and then all of a sudden towards the end it starts spiking up and down. That won't happen. So because of that, they will never have any relative or local extrema. For example, the only way you would get local extrema is if you're going up and then all of a sudden go down to produce that local min or that local max. There's one small case that you can see local extrema with these functions, and that's on a closed interval. For example, let's take this function, for example, and we're looking at, let's go between these 2 points. This is just going to be a restricted domain, so that is really what the function is going to look like there. And so that's really what the function is, which in this case, this is a local min, and this is a local max there. Very rare that you'll see that, but I've seen AP style questions test this concept before. Concave up versus concave down. Logarithmic functions are either always going to be concave up or down. Because they don't switch concavity, there will be no points of inflection. So it's either going to be a downwards U shape or an upwards U shape, like so. The end behavior. For logarithmics functions in general form, so that's going to be a times log base b of x. As you go to the right forever, the outputs will either go up or go down forever. So taking a look at the two functions here, as we go to the right forever, this is going to be shooting up. And as we go to the right forever here, this is shooting down. So this will be going to negative infinity, and this will be going to positive infinity there. Since logarithmic functions, though, have a restricted domain, meaning we can't plug in anything that's 0 or below, they actually will all have a vertical asymptote at x equals 0, unless you move the whole graph left 1 or right 2, something like that. You won't see that right now, so don't worry about too much. And then as a result, the left end behavior will occur at x equals 0 from the right-hand side. So what this is going to look like is if you have a vertical asymptote like so, and then your logarithmic function, let's say, is like this, we would write this as the limit. If we wanted to describe this end behavior, the limit as x approaches 0 from the right-hand side, because we're coming in from the right, and this we'll call this just f of x for now, equals negative infinity. And that would be how we write this end behavior limit statement there. And so it's always going to be one of these two, the limit as x approaches 0 from the right-hand side of the function equals, and then either positive or negative infinity based on what graph you have. So this one goes down, and then this one goes up. And likewise, the limit as x approaches positive infinity of the function equals, and then positive and negative infinity. This one goes up forever, and then this one is going down forever there. So one will either go down and then up, or up and then down there. All right, example number 2. Write limit statements for the end behaviors of each of the following logarithmic functions. So here, as we approach 0 from the right-hand side, we can see this is going to negative infinity. And then this one, the limit as x approaches infinity for f of x is positive infinity. And so pause the video now, try this one on your own. For B and C, this should be positive infinity, and then this would be the limit as x approaches positive infinity of h of x is negative infinity. This should behave like this because a is positive, and so this should be negative infinity, and then the limit as x approaches infinity for g of x is positive infinity there. Example number 3, for each of the following, determine if it's increasing or decreasing, and concave down or concave up. So this is obviously concave up, concave down. This general shape is going to be negative, so it's going to be like this, which is concave up. So we can circle those 3 there. Now, ignoring concavity here, this function is decreasing. It's going down. This one's increasing. It's going up. This one's decreasing. It's going down. So we can circle the correct answers there as well. All right, example number 4. We are given that these functions are logarithmic. Remember what that means is in an xy table, your x's will have a multiplication rule, and your y's will have an addition rule. Find the value of the constant k. For all 4 of these, just by looking at them, we see k is in the x values, so this is going to be a multiplication rule, and we need to figure out what is our missing value for k. And so, for the first one here, we see 1 to 2. This is times 2, and then that rule is going to continuously be applied. And it works with 8 to 16 as well. So 2 times 2, k should be 4 here. So that is our answer for that first one. The next one here, we don't know what this rule is yet, but taking a look at the other values, it's pretty easy. It's times 3, and then it's going to be consistent. So what times 3 gets you 6? That should be 2. So k equals 2 for the next one. This one, looking at this is also pretty easy. Times 2 times 2 times 2. So k should be 8 here. And then the final one, we have e's. So all of them are in terms of e. I know e to the negative second to e to the first is a difference of 3 of them, so e cubed. Same thing with like e to the 7th to e to the 10th. E to the 7th times e cubed is equal to e to the power of 7 plus 3, which is e to the 10th. Remember, you add the exponents. So if we have e to the first times e cubed, this should be e to the 4th. So that is going to be what k is equal to there, e to the 4th. Example 5, let f of x be that function. Which of the following statements about the graph is correct? This, a is negative, so it's just going to behave like so. Once we have this, we see that this function is decreasing, right? The function itself is going down as you go to the right, so we can eliminate a and b. And then the rate of change is going to be increasing strictly because it is concave up. So C should be our correct answer there. All right, the final thing that we're going to talk about today is the domain for logarithmic functions. Typically, logarithmic functions will have a domain from 0 to infinity, right? So we won't start at 0 because there's that vertical asymptote there, but we'll go from 0 all the way to infinity. You can plug in any value of x that's a positive number. However, if we shift this whole graph, let's say 3 units left, our domain is now no longer 0 to infinity. It's now -3 to infinity because every single point moved 3 units to the left. So let's take a look at another example, right? So let me kind of reset this here. We have log base 3x, and then we have log base 3 x minus 4. And so let's graph them both in Desmos right now. This is log base 3x. Here you can see 1 comma 0, you can see 3 comma 1. And then this is the graph of log base 3 x minus 4, or you plug in x minus 4 in for x there. That's the same thing. So this moves the whole graph from here. When you're doing x minus 4, it moves it 4 units over to the right. So remember, horizontal translations are inverse, right? Horizontal translations are inverse. So if you see minus 4, it's actually 4 units to the right. That is very important. What also comes along with it is that vertical asymptote. That vertical asymptote is now being moved 4 units over and now is at x equals 4 instead of x equals 0 there. And so we can see just a good example of this with Desmos here. And so let's take a look at example 6. Which of the following gives the domains for the function g? Here we just have a regular logarithmic function. There's no horizontal translation. The only thing that's changed is our base, but that doesn't affect the domain, right? What numbers can we plug in that doesn't give it 0 or negative? It's just going to be our regular domain. So A is our correct answer here. Now example 7, x minus 6 plus 1, right? What numbers can we plug in that won't give this 0 or a negative number? And that's going to be where this is, we need the inside to be greater than 0, or you could just know that this is just a regular logarithmic function like so. However, because it's minus 6, it's shifted over 6 units. So that vertical asymptote is now being shifted over 6 units because the new graph is going to behave like this. And so our new domain should be from 6 to positive infinity. And so that should be our answer there. One other way to get it is you just need that inside of the parentheses to be greater than 0. And so solving this, add 6 to both sides, you get x is just greater than 6, which is matches with answer choice C. So multiple ways to solve this question. If you have any questions, please come see me during office hours, and I will see you guys later. Thanks.